Good morning and a good day to everyone. My name is Shamishra Parthasarthi. I'm from the Non-Ionizing Radiation Department, Radiation Health and Safety Division from the National Nuclear Agency. My topic of presentation for today would be laser safety, more than meets the eye. Right. My presentation outline will be as following. So first, I'll be doing a brief introduction on the laser, followed by the EM spectrum. So EM spectrum here, it stands for electromagnetic spectrum. IR versus NIR. Technically, IR is ionizing radiation versus non-ionizing radiation. Then I'll be dwelling more on the characteristics of the laser, followed by how the laser works. Next is on the laser applications, the laser classifications, the laser biological effects, especially on the eye and the skin. And then I'll be sharing a bit on the research on laser pointers that I have been doing and is currently ongoing in National Nuclear Agency. And at the end, a final conclusion based on all the results and discussion. Right, so laser is technically an acronym for light amplification by stimulated emission of radiation. So that's the acronym. So if you can see here, the word laser is taken from all the first letter of the acronym, LASER. So technically, although laser has unique properties that make it more hazardous than the ordinary light, it is still just a light. The radiation we are dealing with in the terms of electromagnetic spectrum, so particularly on the non-ionizing radiation spectrum. So the electromagnetic hazards are a function of the associated wavelength, right? A type of wavelength, the intensity in terms of the power density, and also on the exposure duration. One thing to note is there's no any radioactivity or nuclear radiation associated with common lasers. So if you can see in this particular picture, right, so the whole spectrum of NIR is consists of the power lines, right, AM and FM radio broadcasting, mobile network infrastructure, satellites, TV and remote control, visible light, and also ultraviolet. So to put the things into perspective, let us go into the electromagnetic spectrum. If you can see in this particular diagram, this is generally an electromagnetic spectrum. The division is between the non-ionizing energy and the ionizing energy, or you can also call it as non-ionizing radiation and also the ionizing radiation. Right, we will start off with the static electric and magnetic field at 0 Hertz, right, and then followed by the low or extremely low frequency. Generally, it's from the range of 1 Hertz up to 100 kilohertz. The one we are having, the power line, TNB power line, is technically a power frequency of 50 Hertz. And then we move on to the radio frequency and the microwave spectrum, radio, television, mobile phone, smart meters, right? Microwave and also the Wi-Fi. And then we move along, then we'll be going into the remote control, which is utilizing the infrared radiation. Right. So generally the RF spectrum is from 100 kilohertz up to 300 gigahertz. And then we're moving on to the opticals radiation, starting off with the infrared. Technically is from 780 nanometers up to 1 millimeter. So again, based on the NC standard, American National Standard Institute, the wavelength for infrared, technically it starts from 700 nanometer up to 1 millimeter. And then the visible light, it starts from 400 nanometers up to 700 nanometers, right? And then on the UV side, covering from the 100 nanometers up to 400 nanometers, technically the laser, it covers the infrared, right? The infrared spectrum, the ultraviolet, and also the visible light. So technically the visible light spectrum is the spectrum that we could see. It consists of the 7 major colors, red, orange, yellow, green, blue, indigo, and violet. Right. So what's the difference between the ionizing and non-ionizing radiation? So technically a non-ionizing radiation, right, it's an electromagnetic radiation with insufficient photon energy to ionize the matter. So the key point here is insufficient photon energy to ionize the matter. Generally, the division between the non-ionizing NIR and the ionizing radiation is the photon energy of 10 electron volts. So the photon energy of this energy, technically it has a wavelength of 100 nanometers. So from the electromagnetic spectrum you saw just now, right? So it started from the ultraviolet up to the static field. Unlike ionizing radiation, non-ionizing radiation cannot dislodge the electrons from the atoms or molecule with which it interacts. Thereby, it cannot ionize the biological matter. If you can see in this particular picture, so this is the normal concept or the normal picture of a laser radiation warning sign and a non-ionizing radiation warning sign. And this picture here depicts the ionizing radiation warning sign. Right. So to go further into laser, so what we need to do is we need to understand the characteristics of laser. So generally laser, it has only one discrete color or wavelength or a band of wavelength. So focusing on this particular picture, so you can see here this particular laser, it's directional, meaning that this is the particular laser, right? The beam is being energized and being transmitted over a distance. You could see it's directional, meaning that it's only at one specific direction. And then second thing is it's coherent. Coherent meaning that the wavelengths are in phase in space and time, meaning that it's unlike the ordinary light. So here you can see the ordinary light. The ordinary light, the wavelengths are varying, so it's not focused, right? So that's what the saying goes: if you're laser focused, meaning that you're full in concentration. Another characteristics that you need to understand is the operation mode of lasers. Generally, lasers, they operate in pulse mode and also in continuous mode, right? So in pulse modes, technically it operates with less than 0.25 seconds, whereas in continuous wave laser, it technically emits more than 0.25 seconds of wavelength. And important characteristics of lasers are also monochromaticity. So it's monochromatic. So if you can see over here, this particular picture, the light source versus the laser source. The light source, it has a various wavelength consisting of various colors, whereas in the laser wavelength, it only has the green laser wavelength. Right. Next is it's directional and it's collimated beam. Generally, the laser source, right? You can see it's independent of space and time, right? So it's in phase. Whereas for light source, it's not uniform, right? In terms of coherency, right? Again, I can see the laser, it has a very small divergence, right? So when the laser beam is being energized, right, it has a very small divergence. It's highly collimated and the beams spread very slowly, contrary to the normal bulb, whereby you can see all the rays or all the wavelengths are being dispersed without any direction. Right? So the combination of these three properties generally make laser light focus to a spot size that is 1/100 the size of focused ordinary light. So this concludes how focused or how important laser is. Right. So talking about laser, you can't run away from knowing the laser spectrum, right? So again, to recap, on the electromagnetic spectrum, we have radio waves, all right? From this radio waves, TV waves, radar, microwaves, infrared, visible, ultraviolet. So this generally it is in the non-ionizing spectrum, and then X-rays and gamma rays in the ionizing radiation. So lasers, technically they operate in the visible, infrared, and ultraviolet region. So if you can zoom in over here, right? So they operate in the ultraviolet, visible, infrared region. So infrared, it can be divided into near infrared and also far infrared. So if you take into example a ruby laser, so generally a ruby laser, it's with a red wavelength. So technically it operates at 700 nanometers, right? And then another example would be a CO2 laser, which is generally used in industries. So it operates at the 10,600 nanometers, right? One important thing to note is at the frequency or the wavelength from 400 nanometers up to 1400 nanometers, right? These are the wavelength whereby when the beam it enters our eye, it causes a retinal hazard. So the wavelength from 400 up to 700 up to 1400 nanometers is the retinal hazard region. So I'll be explaining more on this retinal hazard region in a couple of slides. Lasers can be categorized according to the type of active medium. So generally they have four main types, the gas lasers, the solid state lasers, the diode or the semiconductor lasers, and finally the dye lasers. So take an example, a helium neon laser, right, which operates at the 633 nanometers. This is generally a gas lasers. And then another example would be Nd:YAG laser. So Nd:YAG laser is generally a solid state laser. So more on the laser classification, I'll be explaining along with my presentation. So when operating laser, we need to understand, or we need to comprehend, three main components of each and every part of the laser itself. The first is the pump source, or in other words, it's an energy source. So the energy source is technically the excitation mechanism that's needed to give energy, or it's as a heart for the laser system itself. So example of excitation mechanism would be optical, electrical, chemical, and also other lasers itself. So the next component of laser is the laser medium itself. All right. So the laser medium is generally the active medium, whereby the lasers are classified according to the active medium. Right. So the active medium is technically the ingredient that's needed to generate the laser itself. Right. So it can be in terms of solid or crystal, gas, semiconductor, or diode, and also in terms of liquid or dye lasers. And then a final component would be the optical resonator. So we have two types of optical resonator, the reflective and also the partially reflected mirrors. Right, if you can see over here, right, this is the high reflectance HR mirror, and this is a partially transmitted mirror. Right. So how it works is the active medium, technically it contains the atoms which can emit light by the stimulated emissions. The excitation mechanism, right, is a source of energy to excite the atoms to the proper energy state. And then the photons, which are traveling back and forth, they collide with the additional atom, creating an intense beam of laser light. And then finally, the optical resonator, it reflects the laser beam through the active medium for amplification. Right. So to understand more, so let us look into this graphical picture. All right. So generally, how lasers work, right? So a laser is created when electrons in the atoms in optical materials such as glass, crystals, or gas absorb the energy from an electrical current or light. So this extra energy, it excites the electrons enough to move from a lower energy orbit to a higher energy orbit around the atom nucleus. So if you look into this particular graphic, right? So the energy from the light, right, it excites the electrons in atoms of optical materials, and then they move to a higher energy orbit, right? So when the electrons, they return to their normal orbit spontaneously, right? Or when stimulated with light of energy, they emit the light particle or in photons. To put the things into perspective, let us go step by step on how the lasers work. So again, as I mentioned in my previous slide, right, there are three main mechanisms, all right, the active medium, right? So the active medium here, it would be the source of the laser itself. Here, the active medium would be the red ruby laser, all right? So the excitation mechanism would be the flash tube, and then we have two mirrors. One is the high reflectant mirrors, and one is partially reflectant mirror, right? So a basic laser, like the one shown in this particular picture, this is a red ruby laser. It consists of a rod made of ruby crystals with mirror on each end and the flash tube, right? So moving on, a burst of light from the flash tube, so which the flash tube, it acts as an excitation mechanism or a source, right? It adds the energy inside the rod. So the rod is generally the active medium. So when the energy is supplied to the active medium, it excites the ruby atoms, and thus it produces light particles. So these light particles are called photons, right? So if you can see in this picture, so a burst of light has been generated in this particular picture, right? And then these photons, it strikes the atoms, right? Creating more and more photons, bouncing back and forth between the mirrors within the rod. So these are the mirrors. So the excitation mechanism, it creates the atom. So the atoms, when the photons, it strikes the atom, right? It bounces back and forth between the mirrors within the rod. All right. So the number of photons, they become so great that when they pass through one of the mirrors, right, which is partially reflective. Again, I like to recap. This is the high reflected mirror, and then this is the partially reflected mirror. So they pass through the one of the mirror which is partially reflective, and then the laser beam emerges. Right. So again, if you see in this particular, I would say graphical video, so you can see how it works. Right. You have excitation mechanism, all right? And then the active medium is the ruby, and then the photons move back and forth, and then the partially reflective mirror and the high reflective mirror, and then the laser beam is being transmitted, right? So generally, this depicts how the laser works, right? Moving on, lasers, they can be used in various applications, all right? So you can name it generally in medical. So in medical, it's used for surgery, surgical procedures, right? For dental treatment, LASIK treatment, right? And then in manufacturing, generally it's very popular in material cutting, right? If you can see in this particular picture, right? It's for material cutting, and then for laser marking system, right? And then in research, so I myself, a research officer in the Malaysian Nuclear Agency, we conduct research on laser safety assessment, right? So we conduct research based on the how we lace the laser to a particular property, and then we can check what's the integrity of the particular structure, right? And then in terms of commercial, I'm pretty much sure that you guys have gone through the laser barcode scanner, right? In hypermarkets, all right, even in provision stores, you have the laser scanners. And then last but not least, during entertainment, so we have the laser light shows, right? So the laser light shows, technically, it's a combination of an array of laser lights. Okay, the applications of the common laser types can be summarized in this particular slides, right? You can see here, we have a laser medium, all right, and then a definite wavelength, right, and also the applications. So if we take the example of first laser medium or the active medium, the diode laser. So generally the wavelength, it varies. The diode lasers are generally used in telecommunications and also in optical communications. Next, we have the Nd:YAG laser, which is a solid state laser. Generally, they operate at the 1064 nanometer, which is in the infrared region. The application normally would be in the material processing, right? Ophthalmology, military weapons, and also in terms of military weapons ranging, right? Then we have the CO2 laser. CO2 laser, generally it operates in the 10,600 nanometer wavelength. Normally it's used in the material processing, right? Material cutting, laser marking, and also in terms of general surgery. We have an excimer laser. So excimer laser is generally a gas laser, right? The wavelength also can be tuned into a multiple wavelength, and it also operates in the UV region. So it's also used in the ophthalmology and also in the photolithography applications. Then we have the argon laser. Argon laser is one of the gas lasers. Generally, they operate in the 488 and 514.5. So generally, it's 488 is in the blue wavelength and 514 in the green wavelength region. So normally used in the ophthalmology and also in the laser light shows. Then we have the helium neon laser, a type of gas lasers. Technically, they operate at the 633 nanometer. 633 nanometers, normally it's in the red wavelength, right? They are used in alignment, scanning, education, and also research. I myself am currently operating the helium neon laser, and I'm currently using it for the research purposes. And then finally is we have the dye lasers. An example of a dye laser is the rhodamine 6G. Generally, it's tunable from 570 up to 650 nanometer, and its applications are normally in the spectroscopy and also in the photochemistry applications, right? So moving on, we go into the laser classification, right? We have 4 main classes of laser. Class 1, class 2, 3, and 4, and then 7 subclasses of laser. So I'll be explaining each and every of the classes as my presentation goes on, right? So the first type is a class 1 laser. So generally, a class 1 laser, they operate in the power of less than 0.39 milliwatt at the frequency, at the wavelength of 500 up to 700 nanometers. All right. So technically, class 1 lasers, all right, their power output is too low to cause any eye or skin injuries. Example is is the power of only a few microwatts or up to less than 0.39 milliwatts, right? So we also have a class 1 product whereby a laser with a higher class, example, a class 4 laser product, right? When it's fully enclosed and it's fully embedded, it's also called a class 1 laser. So it will call it as a laser class 1 with an embedded laser class 4 product. So technically, a good example would be a laser printer. So a laser printer for layman or for normal purpose, right? So we are not exposed to the laser beam itself. So if we are not exposed to the laser beam itself, right, it can be categorized as a class 1 laser. But nevertheless, the moment we remove the enclosure, right, the moment we remove the engineering control measures, the moment we could see the particular laser light, so it goes to a higher class. Either it can go up to class 3B or class 4, right? So the next class 1 laser is the class 1M laser. So the word M here, it stands for magnification. So technically, a laser, a class 1, if you view with an optical aid, all right, if you view with an optical aid, it goes up to 3 milliwatt. So when it goes up to 3 milliwatt, so it's technically a class 1M lasers, right? So class 1M lasers may be a hazard if viewed through any optical aids such as the handheld magnifier, microscope, binocular, and also the telescope. All right. Moving on, we have the class 2 lasers. So generally, the class 2 lasers are visible lasers. They operate at the less than 1 milliwatt from the wavelength of 400 up to 700 nanometers. So their characteristic is generally they operate in the visible range. So as I mentioned just now, with the 7 colors. So example, they operate the red up to the orange, yellow, green, blue, indigo, and violet spectrum. Generally, they rely on blink aversion to prevent any damage. So as we can see this particular laser beam, all right. So how we protect ourselves is we have a blink aversion, right? More on the blink aversion in the next slide, all right. So generally, the class 2 lasers are not safe for viewing times greater than 1/4 second. So this is what I mentioned just now. If you view it more than 0.25 seconds, right? So it may cause harm to the eye itself, right? An example of a class 2 laser is a barcode scanner, the one normally we use in the supermarket or hypermarket, right? Again, as for class 1, we also have a class 2M lasers, all right? Again, the same principle applies. M stands for magnification. The moment you have a magnification or you view it with a optical aid or a binocular or telescope, so it becomes of a higher range of power at 3.5 milliwatt, right? Next is we have the class 3R lasers. So generally, class 3R lasers, they operate at the power of less than 5 milliwatt, right? So an example would be the laser pointer, right? The laser pointer that can be easily available via online and also in a hypermarket. So generally, laser pointers, they operate in less than 5 milliwatt, but nevertheless, there are also laser pointers which are operating at more than 5 milliwatts, all right? And then we have the class 3B lasers. So class 3B lasers are lasers with less than 500 milliwatt, right? Generally, the class 3B lasers are infrabeam and specular reflection hazard, right? This is an example of helium neon laser, the one we are currently using in the lab in Malaysian Nuclear Agency, right? So the helium neon laser, the one we have is generally a class 3B laser. So normally we use it for research purposes and also for training, right? And finally, we have the class 4 lasers. So the class 4 lasers is the highest class and they pose the greatest danger, right? So generally they are intrabeam hazard, even when it's viewed momentarily. And then they are also specular and diffuse reflection hazard. So if we are dealing with the class 4 laser, right, you need to have a laser safety officer based on the NC standard, all right, American National Standard Institute, and also the International Electrotechnical Commission standard, all right. So the key point here is when you're dealing with class 4 lasers, it's a fire hazard and you need to exhibit a greater level of caution. All right. So this particular slide, it summarizes on the characteristics of lasers that we need to know in order for us to do the laser hazard assessment, right? there are two types of refractions. All right, the first would be the specular, all right, or a direct reflection. Right, technically a specular or a direct reflection is when the laser beam is being energized, it goes directly and it hits a reflective surface, example like a plastic or glass or a steel material. So technically the specular reflections can remain hazardous over a great distance. Then the next is we have a diffuse reflection, right? Diffuse reflection is when the laser beam, it hits a rough surface, example like a tabletop or a matte surfaces. So generally, diffuse reflections from low power and medium power lasers usually are not hazardous, right? Diffuse reflection from high power lasers, example from class 4 lasers, it can be very hazardous, right? So moving on, we'll be going more into the laser bio effects. All right. So when you're dealing with laser, two part of human anatomy which is susceptible or which is prone to injury from laser beams are the eye and also the skin. Right. So for the eye, generally the eye, they are extremely sensitive to laser radiation, which could cause permanently damage from either directed or reflected laser beam. So the three major eye structure would be the cornea, lens, and retina. So if you can see in this particular picture, all right, so we have the cornea is the outer layer of the particular eye, all right, lens is where the image which enters the cornea, it gets amplified and it's being transmitted to the retina, right? Macula and fovea is part of the retina system, right? So generally, ocular damages caused by the laser are highly dependent on its wavelength, right? Laser invisible and near infrared spectrum, NIR, from 400 up to 1400 nanometers, normally used in dermatology, can cause damage to the retina itself, right? In terms of UV wavelength, from 100 up to 400 nanometer and far infrared, 1400 nanometers up to 1 millimeter. Generally, this wavelength, it could damage the lens and the cornea. So one thing to note and a key takeaway point is a retinal injury from the laser itself, right? So if let's say a laser is being energized and it's being transmitted in the cornea, and then the moment it goes into the lens, right? The lens, it amplifies or it magnifies the power or density up to 10 to the power of 5 times. So to put the things into perspective, let's see an example. So if let's say a 1 milliwatt per cm square, all right, of power density of a laser radiation, it goes into the eye, all right. So the moment it reaches the lens, then the lens, it amplifies and transmits to the retina. So the power density or the radiant exposure that's measured at the retina is around 100 watt per cm square on the retina, right? So this shows that how dangerous the laser is, right? So that's the thing why we need to exhibit extreme caution. All right, the pictures where it shows the damaging effect of the laser, right? So in these three pictures, all it shows the damage from a laser pointer, right? So if you can see here, all the retina is being damaged, right? So this is a case study of a laser pointer, which can cause a severe eye injury. In the case of a 15-year-old boy who obtained the retinal injuries from a handheld laser pointer, right? Right. So this particular picture, it summarizes the damaging effect of the laser itself. So we have a few types of wavelength from the electromagnetic spectrum. All right. If you take an example of a microwave, X-ray, and gamma rays, so generally this particular wavelength, right? When it goes into the eye, most of the high energy X-ray and gamma rays, they generally pass completely through the eye with relatively little absorption, right? So if you take into consideration of a near ultraviolet, UVA, from 320 up to 400 nanometers, right? So mostly it's absorbed in the lens of the eye itself. So you can see over here, the arrow, the red arrow. So it after it goes from the cornea, it stops at the lens. So all the beam of the laser is absorbed in the lens of the eye itself, right? So technically, when it's absorbed in the lens, right, so it will have a more chronic effect. Example, cataracts. So that's the reason why if we if we go under the sun, all right, so if we are very exposed to the sun radiation, so it's eventually after several years or several I would say 20 to 30 years, there's a tendency for us to develop cataract. Right. So the next is the far ultraviolet, UVB and also UVC. Right. So technically, for this type of wavelength, right, they are mostly absorbed in the cornea itself. Right. So the first line of defense here is the cornea. So all the wavelength from the 280 nanometers up to 320 nanometers, and from 180 nanometers up to 280 nanometers, and finally the far infrared, 1400 nanometers up to 1 millimeter. They're all absorbed in the cornea itself, right? So it causes a keratoconjunctivitis conjunctivitis or snow blindness or Welder's flash, right? So the next is the region that we could see, which is the visible region, right? So normally with the visible region and also the near infrared region, 400 up to 700 nanometers, and also from 700 up to 1400 nanometers. So all the beam are mostly transmitted to the retina. So overexposure may cause flash blindness or retinal burns and also lesions. All right. So next we'll be talking or dwelling more on the damaging effect of skin. Right. So in terms of skin, so the three main layers of skin that we need to know. All right. More fundamental is the dermis, is the epidermis, dermis, and also the fat layer, right? So the laser effects on tissue technically depends on the power density of the incident beam, the absorption of the tissue at the incident beam, the time the beam is held on the tissue, and also the effects of blood circulation. So depending on the wavelength, the beam can penetrate both dermis and epidermis, right? So when you're dealing with lasers in terms of skin, right, it's not as serious as the eye, but then still we need to exert cautions when dealing with lasers, right? So if you take an example, all right, these two pictures, it shows the what a laser could do to our skin itself, right? So the first picture on the left shows the tissue damage from a CO2 laser operating at 250 watt in single pulses. So you can see the traces of burns, right? So the next picture is from the same laser, right? 250 watt laser cutting at 1 inch per second. So you can see over here, it cut through the metal or steel surfaces. So if you could cut the steel surfaces, imagine what it can do to our skin, right? So another example is skin burn from the CO2 laser exposure. So these two pictures generally it depicts the accidental exposure to partial reflection from a 2000 watt CO2 laser beam from metal surface during cutting. So the key point over here is it's just a partial reflection, right? So if it's a partial reflection itself, it can cause this harm, right? So imagine if it's full reflection, right? So now let's move on to the next part of my presentation. So for the next part of my presentation, I'll be sharing my research or case study on the laser pointers or handheld lasers, right? So the objective of my research is generally to determine the wavelength and power of the laser pointers, right? And then next is to compare the laser pointers wavelength and the power with the labels stated in the laser pointers itself. And finally is to perform the laser hazard evaluation from the laser pointer system, right? So I took a sample of 60 laser pointers, all right? It consists of a keychain type, all right? So you can see here, this is the keychain type, and then a pen laser type, right? And then a presenter. So presenter is normally the one we use during the presentation, all right? A small or medium laser type, and then the USB type. So this I've categorized based on their size and also based on their namings itself, all right? So for all the 60 samples, all right, so 24 of the samples were from the USB type, 15 was from the keychain, 4 a pen type, another 4 was on the presenter type, and the 13 was in the small and medium laser type, all right? And then based on the wavelength, technically we had 3 main colors or 3 main wavelength, red, green, and blue. So almost half of the laser pointers that was purchased was operating at the red wavelength, right? 17 was operating in the green wavelength, and also finally the 15 was operating in the blue wavelength region, right? So the first type of measurement is we did a wavelength measurement, right? So this picture, it shows the example of a wavelength measurement from a green laser pointer, right? So we have our own spectrometer system itself. So the laser is being placed over a laser pointer holder, right? So the laser is being energized, all right? And then the power is being transmitted to an optical detector or optical sensor from a spectrometer system. So what the spectrometer system does is it converts the optical output into electrical output, and then the wavelength from this particular laser could be recorded, right? So when we could check, so this is how it's being done. So we go here, and then once we go at this particular software system, the software, it records what is the peak wavelength. So for this type of laser pointer, so the peak wavelength was detected as at 532.62 nanometers. So it's roughly around 533 nanometers, right? So again, we did for each and every part of the laser system, and then in some cases we detected 3 types of wavelength, right? So other than the green wavelength, right, we also detected the second harmonic or the second peak wavelength at 806.34 nanometers, and also the third harmonic or the third peak of 1064 nanometers. So if you can see here, this is a visible light, the one that we could see, and the second and the third laser radiation wavelength, right? These are operating in the infrared region that's it's invisible to our naked eye, right? So the next part of our measurement is on the power measurement. So before going to the power measurement, so this picture, it shows the how the wavelength measurement, how the measurement is being done. So this is the top view of the measurement. So you can see how intense the light, the green light from the laser pointer itself, right? So when we did this type of safety assessment measurement, we ensured that we wore the correct laser eyewear protection or the laser safety goggle, right? So the next part of the research is to do the output measurement, output power measurement from the green laser pointer itself, right? So if you can see in this particular picture, the same experimental setup is available. The only difference is the detector, all right? So previously we used the spectrometer detector, but now we replace the spectrometer detector with the laser power meter detector, right? So the same principle applies. The laser is being energized, and then the energy is being transmitted into the detector or the sensor of the laser power meter. The power meter converts the optical output into the electrical output, and then we have the particular result over here. So one thing to take note is we also did a comparison between the measured wavelength and power with the one labeled in the laser pointer itself, right? So if we take an example over here, right? So this is the way how we measure. We place it in the laser pointer holder, right? So we try to magnify this particular area, right? So we get the whole picture of the laser pointer, and then we magnify the warning sign itself, right? So the moment we magnify the warning sign, so it's already stated here, the maximum output power, the one in the label, was at less than 5 milliwatt, and then the wavelength is stated at 532 nanometer plus minus 10. So plus minus 10 is it could range from 522 nanometers up to 542 nanometers. So based on our analysis and also our observation, right, we noticed that only 10% of the laser pointers were showing the correct wavelength compared with the label. So the remaining 90%, right? So for this particular case, right, based on the assessment conducted on 60 laser pointers, right, only 6 was showing the correct wavelength, right? And then whereas the majority of 54 laser pointers were showing the incorrect wavelength. So again, with the same principle, we compared the output power, we compared with the label itself, right? So again, here, more than half, right, almost 60% or 58%, it was showing incorrect power measurement, and then only 42 was showing the correct power of the laser. So this comes to the point where we need to do a laser hazard evaluation or hazard analysis. So when you are doing a laser hazard analysis or safety assessment, two things that need to be taken into account is the maximum permissible exposure, MPE, and also the nominal ocular hazard distance. So for the first hazard analysis criteria, the MPE, so generally MPE is the level of laser light to which a person may be exposed without risk of injury. So technically MPE is a dividing line between a safe and the potentially harmful exposure level. So in layman's term, you can call it as a safe level or a laser safety speed limit. Example, if you take to put the things into perspective, right? So if you can see over if you can see the picture over here, right? So you have the MPE level here, and then the one in green is generally safe, and then above this particular MPE line is technically overexposure, and this could probably cause harm to the retina, our retina, right? It is. So the MPE is calculated based on the wavelength and also based on the area of the limiting aperture of the eye. So technically, the area of limiting aperture of the eye is we take the diameter of the eye, right, and then we calculate the area which it goes at up to 0.3819 cm square, right? So the power density, all right, can be calculated from the radiant power divided by the area of the limiting aperture. So I won't dwell more into this because this involves a more complicated calculation. So based on our calculation, the MPE from the 400 up to 700 nanometers at the operation time of 0.25 seconds for the visible wavelength, it's calculated as 2.55 milliwatts. So how do we get, or where do we get this particular value? So we get this particular value from the American National Standard Institute NCZ 136.1 intrabeam table. Again, I won't go more into this technical part, right? So based on this, we can go into this visible range, right? We can check the intrabeam, right? Everything is already set. So the thing is, we need to plug in the value and calculate what is the duration and how we could calculate the MPE, right? So based on that MPE, so we'll try to calculate the MPE from the wavelength and also from the duration. So for the second part of the hazard analysis, we go into the nominal ocular hazard distance, NOHD analysis. So nominal ocular hazard distance, or in short, NOHD, is generally the distance at which the beam irradiance, right, or radiant exposure, it equals the appropriate eye or the corneal MPE. So if you look at this particular picture, right? So the laser is being energized, and then the laser beam is being transmitted, right? So the NOHD area is the one when the energy is at MPE. So if it's small above the NOHD is considered as a safe zone. So again, the formula to calculate the NOHD is equivalent to 1 over divergence, parenthesis, right, bracket 4 times to the power of 4 times the power and divided by the pi and also MPE, and then bracket you minus with the a square is the initial beam diameter, and the whole thing you square root it. Again, I won't go into detail. I'll just present the results to you, to each and every one of y'all, right? So to put the things into perspective, so this summarizes the MPE and the NOHD. So as I mentioned in a couple of slides ago, so generally MPE is a safe level, right? It's a safe level in terms of irradiance, and NOHD is the safe distance itself, right? So if you can see in this particular picture, right? So when the laser is being energized, right, and then when the transmission is at a full horizontal line, right? So you can see over here, so the safe distance is after the MPE over here. So this is the MPE dividing line. So after this particular line, this is the safe distance. Whereas at this particular point, all right, so if the nearer you are to the laser itself, right, so the more dangerous or the more prone for you to get a retinal injury, right? So based on this safety assessment from all the 60 laser pointers, right, we have calculated based on the maximum permissible exposure, right? So you can see here in this particular graph, laser pointer 1 up to laser pointer 30, and then in the next graph, laser pointer 31 up to laser pointer 60, right? So you can see almost all I would say most of the laser pointers, they exceed the maximum permissible exposure value of 2.55 milliwatt per cm square. So this is the dividing line, right? Dividing line, and then most of it exceeds the MPE level. So based on the safety assessment conducted, right, only 20% of the laser pointers, or in this particular case, only 12 units of laser pointers were emitting the laser radiation below the MPE, whereas the 80%, right, or the majority of the laser pointers, 48 laser pointers were emitting above the MPE. So what does this conclude? Meaning that the moment you have 80%, when it's emitting a laser radiation above MPE, meaning that it's very dangerous, right? So the moment it goes into the eye, the chances of us to get permanent or temporary retinal burn or retinal injury is very high, right? So it doesn't mean that if the laser is operating below at the MPE, it's safe. Again, if it's safe, if we temporarily or we accidentally view. If let's say we are to view it directly, again, there's chances for us to get a retinal eye injury. Right. So this graph again, it summarizes the nominal ocular hazard distance, the distance from each and every lasers. So if you can take into example, this is the lowest emitting keychain, right? So at this particular laser pointer, so the NOHD would be at 5.9 meters, meaning that after 5.9 meters, we can view the laser beam directly without causing any harm. But then we also have the highest power of a USB laser, whereby the NOHD of this particular laser is at 130.2 meters, meaning that the laser could only be safe to be viewed directly after this particular distance. So imagine how far the laser could go, right? So in summary, right, it can be deduced, or it can be concluded that only 20% of the laser pointer that have been assessed is safe, whereas the 80% of it are unsafe, right? And then in terms of the NOHD, right, 21 of the laser pointers, the NOHD distance, right, it is below 10 meters, right? 26 was in the range of 10 meters up to less than 50 meters. 12 was above 50 to less than 100 meters, and finally one laser pointer, right, the USB laser pointer, the NOHD was above 100 meters, right? So again, to recap, this really shows that whenever you're using a laser pointer, right, you should also exert caution, right? So this is technically a minor recap of what I've explained just now. A laser pointer which is operating in the visible range, right? Technically, most of the beam are transmitted to the retina itself. Overexposure may cause flash blindness, retinal burns, and lesions, right? So this picture, it shows the hazards of retinal injuries from a laser pointer itself, right? If you can see all the three pictures, generally it shows all the retinal injuries and retinal burn, right? So I will just go to one case. So technically, the first case would be a 9-year-old boy who suffered serious permanent eye damage after repeatedly gazing into a green beam from a laser point. It occurred in Greece in 2018. So the keyword is repeatedly gazing, right? So this is it's very dangerous, right? All right, and then for the second case, it's a 14-year-old teen permanently damaged his retinas by deliberately shining a laser pointer into his eye for a very brief period. So key point over here is a very brief period. So even if it's a very brief period, and then the moment our eye captures the particular laser beam, is transmitted into the retina. So the chances for us to get a retinal injury or a retinal burn is also high. So the third case is a case of an 11-year-old boy who suffered irreparable damage from a laser pointer deliberately aimed at close range by his classmate. So again, the key point here is close range, right? So if you can see in this particular picture, this is what happens, during a riot in one of the countries, right? So they use a particular laser pointer to blind us. So this situation is called flash blindness, right? So the second part is a simulation of how or what the pilot sees or what he's exposed to when a green laser pointer is aimed directly at him. So to put the things into perspective, let us see this particular animation. So this animation is based from a flight simulator, right, showing the visual effect of a 5 milliwatt green laser pointer. So it's at the landing bay, right? So the moment before he lands, he could not see the runway. So if this happens, so the chances for the pilot to land this plane is also very, it's very, very challenging, right? So again, what can be deduced or concluded from this particular research is the light from a laser pointer is at a wavelength to which the human eye is most sensitive, right? So if you can see over here, the visible range from 400 up to 700 nanometers, right? And then the retinal hazard zone from 400 up to 1400 nanometers, right? So if it's in the visible range, right, from 400 up to 700 nanometers, the retinal absorption is highest at the green wavelength, I would say at around 550. So that's the reason why a green laser pointer or GLP, it appears far brighter than a red laser pointer that emits the same optical power, right? So the direct exposure of the eye to the green laser pointers seems to be relatively rare, but then cautions or methods should be taken in order to protect our eye from very strong visual intensities, right? So we have our inbuilt blink responses, but nevertheless, precautions should be taken, right? So to conclude the research on the case studies from the laser pointers, so what we need to do is generally we need to purchase a low power laser pointers, if preferably of class 2, right, of less than 1 milliwatt. So how do we know whether it's less than 1 milliwatt or not? So the first thing is we need to check the label itself. So if let's say if the label is not stated anything in the label, so it's better for us not to buy that laser pointer itself, right? Second is compared to green laser pointer, try to choose a red or orange laser pointer from the wavelength around 633 to 650 nanometer. So from the graph, you could see this particular wavelength, all right? So the intensity captured by our retina is not as high as the one captured by the green wavelength, right? So the next is you need to have an on and off switch, right? Meaning that you need to have not a permanently on type of laser pointer, example like a torchlight. So the moment it can only be turned on if you press. So the moment you remove your thumb or a finger, it will automatically off. So you need to buy or purchase that type of laser pointers. And then fourth is you need to purchase from a reputable dealer. Don't purchase or use an unlabeled laser pointer. The fifth important point would be to aim the laser pointer only at the presentation screen itself. So point only at inanimate objects, never at a person or animal, regardless of the power. So here we can see there's a very a viral video of a person who's playing with the laser pointer. He's transmitting to the cat itself. So this is very, very dangerous because when the laser beam it goes into the eye, so the chances for the animal to sustain a retinal injury is also very, very high. So do not aim a laser pointer at a shiny or mirror-like surface. Again, this is pretty much clear-cut. I've explained in my previous slide, right? And then do not allow children to use a laser pointer unsupervised, right? So as parents, we need to supervise them. Never aim a laser beam at an aircraft, a vehicle, or towards strangers. So in other words, don't annoy people with laser beam itself, right? So so the conclusion of laser safety, right, more than meets the eye is if the laser beam is strong enough to light a cigar, meaning that it's strong enough to burn your eye itself, right? So the next key takeaway message would be a laser injury is permanent. So we need to exert preventive measures and also exert cautions, right? So the final point would be the person operating or using the laser always has the primary responsibility for all the hazards associated with the laser use itself. So that's my presentation. So I'll conclude with the final keyword. which is work safe with lasers, because when working with lasers, you need to always ensure a safe working environment for visitors, colleagues, and also yourself, right? And then think before you act. That's all from me, right? So again, if you have any questions, you can directly email me at shamish@nm.gov.my. So that's all. Thank you and have a great day ahead.